Okay, people have some questions on some examples of some problems, so I'm going to go ahead and step through some since I don't have my notes currently available for you. So let's just look at one. Let's look at number 13, section 5.2. So we've got f of x equals natural log of cubed root of 4x minus x squared. So if I want to take the derivative of that, we're trying to find f prime at x. So what I'm going to redo, I'm going to rewrite this as the natural log of 4 minus x squared to the 1/3 power. So what we can do here is we can use log rules. So anytime we use log rules to make life easier, I want to do that. So I'm going to drop that 1/3 down in front. And so this is going to be equivalent to 1/3 natural log of 4 minus x squared. Now remember, I have not taken the derivative of this yet. This is simply what f of x is. Okay. So when I take f prime at x, it's going to be derivative of constant times the function is the constant times the derivative of the function. Here's my function. So the derivative of the natural log is 1 over, derivative of the natural log of x is 1 over x. So this is 1 over 4 minus x squared. But what we need to realize here is that this is natural log of a function. So by the chain rule, I got to take it times the derivative of what's inside, which is minus 2x. So simplifying that now, it's going to equal f prime is going to equal then minus 2x over 3 times quantity 4 minus x squared. So that should be what f prime at x is. Okay, so that's number 13. Let's do another example. Let's do something similar. Let's do number 25. Let's see what that one looks like. Here we have h of x equals x over the natural log of x. And what we're trying to find here is we're trying to differentiate the function. So we're trying to find h prime at x, or dh dx. So however you want to write that. Well, what I have here is I have a quotient, so I got to use the quotient rule. So I'm going to put quotient rule right here. It's going to be the bottom one times the derivative of the top one. The derivative of x with respect to x is 1 minus the top one times the derivative of the bottom one. Well, the derivative of the bottom one would be the derivative of the natural log of x, which is 1 over x. And then all over the bottom one squared, which is natural log of x, quantity squared. Okay. So what I can do is a little algebraic simplification here. This x and this x cancel the ones. And so what I have is this is equivalent to the natural log of x minus 1 all over the natural log of x quantity squared. And once again, this is h prime at x. Now, one thing that you might think about is, could I use the log rule here with this squared? Can I drop that down in front here? The answer is no, because remember we have the natural log of a the r power. So the r power is really with the a, and then that can drop down in front as r of a. We cannot do that here because it's quantity squared, which is actually equivalent to the natural log of x times the natural log of x. And that's not what we have. If I had natural log of x squared, that would be natural log of x times x, and that is not the same thing as what we have here. So the answer is no, I cannot use the power rule here. So this is actually what the answer would be for h prime at x for number 25. Okay. So clear that, do a couple of more here. Let's do number 27. How about we do number 27 here? So 27 looks a little bit awkward. We've got g of x equals the natural log of the cubed root. They like these cubed roots. So cubed root of x plus 1 over x squared plus 1. Okay, so what I'm going to do is I'm going to rewrite this. We're going to want to find g prime at x, or dg dx. So I'm going to rewrite this as the natural log of x plus 1 over x squared plus 1 quantity to the 1/3 power. Now I can use the log rule, the power rule for logs, and I can drop that down in front. So g of x is equivalent to 1/3 natural log of x plus 1 over x squared plus 1. And then what I would like to do now, because if I take the derivative of this, the derivative of the natural log would be 1 over this thing, which is a fraction, which is fine because I could flip it, but then I'd have to take it times the derivative of what's inside, which is using the quotient rule as well. So instead of doing that, what I want to do is I want to rewrite this again using log rules. So this is equivalent to 1/3. So for this part right here, natural log of a divided by b is the natural log of a minus the natural log of b. So this is going to be the natural log of x plus 1 minus the natural log of x squared plus 1. And so it's 1/3 that quantity. So now I'm going to be able to find g prime. So that implies that g prime at x, once again, the derivative of a constant times the function is the constant times the derivative of the function. And here my function is a difference. The derivative of the difference is the difference of the derivatives. So the derivative of the natural log of x plus 1, the first part, is 1 over x plus 1 times the derivative of what's inside. Well, the derivative of what's inside there is just 1 by the chain rule. And then minus the derivative of natural log of x squared plus 1. Derivative of natural log is 1 over that thing, so act like it's okay. But then times the derivative of what's inside. So the derivative of what's inside there is 2x by the chain rule. So I got to attach that. And then now I can go ahead and simplify this stuff a little bit. So it's going to be 1/3 times the quantity 1 over x plus 1, and then minus 2x over x squared plus 1. And this should be the answer. I didn't look in the back of the book to see, if that's exactly what they have, or if they got a common denominator inside and did some simplification via algebra. But this answer for me is good enough because nothing's going to cancel or simplify. Okay, so some good examples there. Now let's go to one that says find dy dx by implicit differentiation. So let's go ahead and do, let's go ahead and do number 31. Number 31 says find dy dx by implicit differentiation. So what we have here is we have x's and y's in the problem in different places. I'm going to change, I'll go ahead and do this one. Actually, what I'm going to do, instead of 31, I'm just going to make up my own. I'm going to say plus x squared plus y squared equals 2. Okay, so really what I want to do to both sides is I want to take the derivative of this thing with respect to x. Okay, so you can do the same thing to both sides of an equation. So when I do that, before I do that, I actually want to use my log rules if I can to make life easier. So here I've got natural log of x times y. So natural log of a product is the sum of the natural log. So that's going to be natural log of x plus the natural log of y. That's going to be a little bit easier for taking derivatives. And then plus x squared plus y squared all equals 2. And once again, I'm taking the derivative with respect to x of that whole thing. So when I go ahead and take the derivative now, let's go ahead and do that for each part. The derivative of the sum is the sum of the derivatives. So I'm going to take the derivative of each part here with respect to x. So the derivative of the natural log of x is 1 over x, plus derivative of natural log of y. Remember, y is some function of x in theory. So basically, I'm going to act like it's okay. It's 1 over y, but because there's a y, not an x, I need to attach a dy dx. So that's the process of implicit differentiation. And then plus the derivative of x squared with respect to x is just 2x. And then the derivative of y squared with respect to x, you act like it's okay, so it's 2y to the first. But because there's a y there, I got to attach a dy dx. Now here's the tricky part that's actually really easy, but the derivative of any constant with respect to any variable is going to be 0. So don't forget that. Don't leave that 2 there. We need to make that a 0 because the derivative of a constant with respect to any variable is 0. Now, notice I've got an x in the denominator and a y in the denominator. Kind of makes things a little bit messy. Clean this mess up a little bit. What I could do is I could multiply everything through by the least common denominator, x times y. And if I multiply this through times each term, I got 4 terms here. Then what I'm going to do with the first one, this is equivalent to the x's would cancel, so it'd be equivalent to y plus, and the second one, the y's would cancel, and it'd be x, and then still times the dy dx, and then plus, now it's going to be 2x squared y, and then plus 2xy squared dy dx, and that's going to equal 0 yet. Okay, so that actually, let's just do implies this. Okay, so we have right now, we have all this stuff. And so really with implicit differentiation, we have 2 types of terms. We've got terms with dy dx's in them. So we want to get all the dy dx terms to one side and everything else to the other. And so what I need to really do here is I need to just give myself some room, ideally. So I'm just going to try and erase the top without taking too much time here. And so what I want to do is I want to rewrite this and get all my dy dx's to the left, everything else to the right, and then I'm going to factor out a dy dx, and then I'm going to divide both sides by that. So let's go ahead and do that. And I'll go back to blue here on top. So I've got x dy dx is still on the left side here, and I've got plus 2x squared, plus 2xy squared dy dx. So that's a dy dx term. That stays on the left, and get everything else on the right by subtraction. So this equals minus y minus 2x squared y. So this term and this term need to go to the other side by subtraction. And so I'd have this. And then what I can do is I can take my dy dx that's in every term on the left, factor it out, and I'll have dy dx times the quantity of what's left, which is x plus 2xy squared, and that equals minus y minus 2x squared y. And then it looks like I'm going to need some more erasing going on to give myself some more room. And so what I can do to both sides then is divide by the terms that are attached by multiplication to the dy dx. So if I do that, let's go back to my drawing here. So really what I want to do is I want to divide both sides by this. So that was minus y minus 2x squared y on top, and then I'm divided by x plus 2xy squared. So really this is my answer here. Sorry, that's supposed to be a y squared. But really what we want to do here is we want to make sure, that's not a very good squared there. So let me do that again. Anyway, what I want to do is I want to make sure nothing factors are canceled out. So what I can do is I can factor out a least common multiple of both sides here. So on top I could factor out a minus y. So dy dx on top, factor out a minus y, and I'm going to be left with 1 plus 2x squared. And on the bottom, I have an x in common, so if I factored out an x, I'd be left with 1 plus to y squared. So close but no cigar, nothing ends up canceling here. So this is another alternate version of this one right here. So this is a correct answer. This is also a correct answer that's factored, but we can see here that nothing is going to cancel out. So this is what dy dx is by implicit differentiation. So hopefully that a couple of these examples help you on that, and we'll just kind of go from there. I could look a little bit at one more example of graphing or two. So let me do that. Let me just clear this whole board because it was getting pretty full. Let's just do a couple examples of graphing. So example, if I want to graph y equals natural log of x plus 1. Well, what's that? Natural log of x is the base graph. We know what that looks like. Natural log of x looks like this. Okay, and then crosses at 1, doesn't touch down here. So if I want natural log of x plus 1, that's just an upshift by 1 unit. Okay, so that's an upshift. So basically, instead of over 1 up 0, I'm over 1 up 1. It's going to be the same type of graph here. Doesn't touch the axis. I accidentally touched it. But it's the same graph, just shifted up 1 unit. Okay, so basically, if I was rewriting it, it'd be up a little bit higher where 1, 1 is on your graph. Okay, I'm going to do one more. If I've got example, natural log y equals the natural log of x minus 1, then basically I got to do something first. The question is, where does this equal 0? That equals 0 when x equals 1. Okay, so what is the natural log of 0? Well, the natural log of 0 is explodes to negative infinity, right? So where is that going to occur? That's going to occur when x equals 1. So instead of occurring at 0, really what I have is I have a vertical asymptote at x equals 1. And I would be approaching this negative infinity as x gets closer to 1 from the right. And so it's going to look like the natural log graph here. And then instead of being over 1 up 0, now I'm going to be over 2 up 0. And if it helps, what do you plug in? We know that the natural log of 1 equals 0. So what do I plug in to get 1 here? I'd have to plug in x equals 2 to get a height of 0. So 2, 0 is going to be on my graph. It's going to be the base graph. Basically what this ends up being is a right shift. So hopefully all this helps you complete some of the evens that are going to be due for you. So take care. Thanks.